In this lesson, we are going to talk about rate of change for a linear function. But first, let's review what is rate of change. So back in Unit 2, we talked about finding the average rate of change in a function. And we used all kinds of functions, right? And so what was really important about rate of change is we were given two pieces of information that we wanted to find the rate of change between. So in this example, it's f of -3 to f of -5. What is the -3 and the -5? They're inputs. So we talked about in Unit 2 having a table with our x and y, or our input and output, and then we put our inputs in, and now I've got to figure out what are my outputs. How do I find the outputs? We're going to plug them in and substitute, and then simplify. So anywhere I see an x, I'm going to plug in my two inputs. So I'm going to start with -3 squared plus 4 times -3 minus 7. And if we do the math, it's a +9 plus -12, which will be a -3 minus 7 is a -10. You can use your calculator, or you can simplify it just like I did. What is the output for the input of -5? Well, if we plug in -5 squared plus 4 times -5 minus 7, -5 squared is a +25, plus 4 times -5 is a -20. That gives me a +5, minus 7 will give me a -2. Now we are going to find the rate of change. So all of this was just evaluating. Okay, now we actually have to do the rate of change part. And so how do you remember the order to do rate of change? Rate of change is our change in y over our change in x. Okay, so that means we're going to be subtracting. We're going to subtract our y's over our x's. So I'm going to say -10 minus -2 over a -3 minus -5. Now in both of these, I do have a state change, so this actually becomes plus a positive. It's not always plus a positive. Remember, you're finding the difference, you're subtracting. Okay, so what do we get here for the rate of change? We get a -8 over +2, which becomes a -4. Okay, and that was what we did when we were just looking for that average rate of change, no matter what type of function we have. Today, we are going to talk about specifically linear functions, okay? And the really cool thing about linear functions is that they're constant, okay? It is constant when you're talking about the rate of change for a linear function. So it doesn't matter what 2 points you're going to select. Any 2 points in the table, any 2 points on a line, it doesn't matter. It's a constant rate of change. If you think about what a linear function looks like, you have your coordinate grid, and then here's your function, okay? Anywhere you look, your rate of change, your vertical rate of change is going to be the same, okay? There is no weird change. If you look here, at some point, we have a negative rate of change, and then it changes and it's positive. That's not constant. This is constant all the way from -infinity to +infinity. Okay, so let's look at what that means. If we look at example 1a, we're looking at the slope of a linear function. Now, slope is the same thing as rate of change. Okay, so anytime you see slope, it's usually specific to a linear function. Okay, but it's just rate of change. All right, so we've got to make our table with our x and our y, and remember, it doesn't matter what your inputs are, because this entire table, the whole thing, is a constant rate of change, so we get to pick. So I like to choose small numbers. I like to deal with 0. I don't like to deal with a lot of negatives. So I'm going to pick numbers down here because none of them are negative. So I'm going to use my inputs of 3 and 4. And so that means that I have an output of 0 and an output of 2. And then remember, is rate of change the change in y over x or the change in x over y? It's the change in y over x. So what is your fraction going to look like? We're going to subtract down, so I'm going to say 0 minus 2 over 3 minus 4. That becomes a negative 2 over negative 1. What does that reduce to? 2. And it doesn't matter. You could pick 2 points from anywhere in the table and you will get that same answer. Let's look if I had just selected these two. Okay? I'm going to have negative 8 minus a negative 6 over negative 1 minus 0. State change, change. So I get a negative 2 over negative 1, which guess what? Reduces to 2. What if I selected these points right here in the middle? I'd have negative 4 minus negative 2 over 1 minus 2. State change, change. I get a negative 2 over negative 1, which is 2. It doesn't matter. Any 2 points you pick on this table will give you the same rate of change. So, why don't you take a look at this and try one on your own? If you make your table x, y, and you pick any 2 points, okay, any 2 points at all, I'm going to choose these points right here because they're my smallest values that are not negative. So I have 3 and 1 and 5 and 4. They're going in my little rate of change table. It doesn't even have to be 2 points that are next to each other, by the way. You could pick the very first point and the very last point. That's okay, as long as you have 2 points from the table. So, back to our rate of change. I set up my fraction. I'm going to subtract down, so I have 1 minus 4, and then I subtract down again. I have 3 minus 5. This becomes a negative 3 over negative 2. I have to reduce it. Negative over negative becomes a positive 3 over 2. And that's it. Let's look at example 2a. Now this is finding that rate of change from a graph. Again, it doesn't matter what inputs you choose, okay? All across here, you're going to see that the rate of change is constant. There's also, when you're given a graph, 2 different ways you could do this. So when we're looking at this, I'm going to go ahead and make my table, x and y. And I'm going to pick this point right here and this point right here. So then I need the coordinates. For this point, it would be a 0, and then we're counting up 1, 2, 3, 4, 5, 6, so 0, 6. For the second point, we're over 1, 2, 3, so 3, and up 1, 2, 3, 4, 5. Same idea. We're going to subtract down. This is all about rate of change, remember. So 6 minus 5 over 0 minus 3. I end up with 1 over negative 3, which you can leave like that, or we can just say it's a negative 1/3. Now, the other way you could do it is just to simply look, is this line increasing or decreasing? It's decreasing, which means it's going to be a negative slope. Okay, decreasing is a negative slope. Which means, what if the function was increasing? It would be a positive slope. Okay, but this slope is decreasing, so we know our slope is going to be negative. Okay, let me clean some of this off here. So then, I'm going to pick 2 points on my graph, any 2 points at all. Let's say that one and this one. Any 2 points. You could pick 2 points right next to each other. You could pick the first and last point. It doesn't matter. And I like to draw a right triangle staying along the lines that are already there on the graph between those 2 points. And then I'm going to count how many spaces up and down. So here is 1, 2. And over here is 1, 2, 3, 4, 5, 6. And so if you think about, remember we talked a lot about slope being rise over run, right? Which one of those, 2 or 6, would be my rise? The 2, which means that what is the run? 6. And then we reduce that and we get a negative 1 over 3, which was the same thing, but I didn't have to do any math. So you can choose. You can either count the slope on the graph, or you can find the slope using the algebra. You want to try one? Let's do it. Try this example, example 2b. So if I were to count the slope, I can see that this line is increasing, so I know it's going to be positive. Okay? It's a good start. I know the slope is going to be positive. Then I'm going to pick 2 points, and it truly does not matter. Remember, a linear function is constant. It does not matter what 2 points you pick. I'm just going to pick this point and this point. So I'm going to draw that little triangle and count my spaces. 1, 2, 3, 4 over 1, 2, 3, 4. So in this case, our rise over run is the same, right? We have 4 over 4, which reduces to a positive 1. Now let's see if I do the math if we get the same answer. Okay? So I'm going to pick this point and this point. Remember, I like positive numbers, and everything in that quadrant will be positive. So here's my x and y. Looks like I have the point 1, 2, and I have the point 4 and 6. Okay? So if we set up our math, remember we subtract what over what? It's always y's over x's. So 2 minus 6 over 1 minus 4. I get a negative 3 over negative 3, which reduces to positive 1. Which method do you prefer? The algebra or the counting? No matter how you do it, as long as you're doing it correctly, you'll get the same answer. All right, let's look at this one. This one always throws students off, but it's actually way easier than it seems. You just have to remember to make your table. Okay? And let's take a point. Which letter, B or E, is the x value? B is the x value, which means E is the y value. How about this point? What is the x value? I, which means T is the y value, or input-output maybe. So then let's go ahead and do our subtraction. What am I going to put on the top of the fraction if I'm subtracting down? E minus T. And so what goes in the bottom? E minus I. Good. Guess what? Do you know what E minus T is? Do you know what B minus I is? No. So that's our answer. It's that simple. There's no math to do. So try example 3b. Remember that we want our input-output. And you've just got to take your points, and it doesn't matter. I should point out that this example, you could also say T minus E over I minus B. That would be okay too, either one of those. So here I'm putting in my 2 points, okay? And it doesn't matter if you flip those, you can get the same answer, okay? So if we subtract down here, I'm going to say S minus P over R minus N. But what would it look like if we subtracted up instead? N minus R would go in the top or bottom? N minus R goes in the bottom. which means what goes in the top? P minus S. So either one of those would be okay. They mean the same thing. Okay? Cool. Let's try example 4a. In this example, we are given an equation in slope-intercept form. What is so important about slope-intercept form? What is slope-intercept form? Y equals mx plus b. What does the m stand for? And what does the b stand for? M stands for slope, and b stands for y-intercept, but we're asked for the slope, which is which letter? M. And what value is in the m position in this equation? The 2/3. So that means our slope is 2/3. We're done. That's it. So try example 4b. What's the slope of this linear function? This, again, is in slope-intercept form. And slope is which letter? It's m. So what number is in the place of m in this function? -2. So our slope is -2. That was easy. So example 5 is very similar, except that this is not in slope-intercept form. This is in standard form. And so we've got to put this into slope-intercept form first, which means I have to solve it. So we're solving for y. So I'm going to inverse the 3x first. That leaves me with a -7y equals a -3x plus 49. We're going to divide by -7. Okay, so now I have y equals a positive 3/7x minus 7. What is the slope of this linear function? If this is now in slope-intercept form, remember that which letter is slope? It's m. And what number is in the m position? The 3/7. So our slope is 3/7. Why don't you try the last one? So we've got to solve for y, which means I'm going to inverse the x term over here by subtracting. And I'm subtracting because this is a positive. That leaves me with a -3y equals, we're trying to put this in slope-intercept form. So we're putting the x first. Divide by -3, divide by -3, divide by -3. So I get y equals a positive 5/3x minus 6. This is slope-intercept form. And slope is m. So what number is in the m position? The 5/3. And that's it. Let's try some practice problems.